Hello everyone, today we will start the introduction about the Ashford Institute method for the pavement design. The Ashford Institute method was developed based on empirical data from WSHO, ASHO, and British road test results, and the method was further revised with mechanistic and empirical analysis. In this method, we would like to design the pavement structure which is thick enough to limit the repeated horizontal strain at the bottom of the asphalt concrete to acceptable levels. In that sense, we can avoid the fatigue cracking. Also, we want to restrict the repeated vertical strain at top of the subgrade to acceptable level so that we can avoid the permanent deformation. To achieve this objective, in the design, the alligator cracking is limited to 20 to 25% of the pavement surface, and the rotting is limited to 12.7 mm over the whole design period. The figure here shows the vehicle load applied to the pavement structure. The load will be transferred from the surface of the pavement structure to the bottom and reach the intersection between the pavement structure and the subgrade. Generally, in the AI method, we have to analyze the compressive stress applied at the intersection between the pavement structure and the subgrade. Also, we are interested in the tensile stress applied at the bottom of the asphalt layer. Compared with the MTO routine method, the AI method is more realistic and more accurate. In this method, the design is based on two critical conditions: fatigue cracking and rotting. Usually, the fatigue cracking will develop under repeated loading if the horizontal stress, which is the tensile stress, at the bottom of the asphalt layer is excessive. Usually, the rotting or the permanent deformation will occur at the surface of the asphalt layer from overloading of the subgrade. If the vertical compressive stress, that is epsilon c, at the surface of the subgrade is excessive. Also, the rotting can be caused by the construction-related problem. For example, if the compaction is not appropriate, then it can easily create the rotting to the pavement structure. The AI method is widely applied for a lot of roads in Ontario. It can also be applied for the pavement with different structures, such as the asphalt concrete surface over asphalt concrete base, which is the full depth pavement. It can also be used for the emulsified asphalt concrete surface over untreated granular and untreated aggregate base and subbase. The two figures here shows the full depth and deep strength asphalt pavements applied in Ontario. The figure on the left shows the structure for the full depth asphalt pavement. It consists of the asphalt concrete surface and asphalt concrete or emulsified asphalt base. It does not have any granular subbase. The tensile stress and compressive stress are applied directly at the intersection between the asphalt concrete layer and the subgrade. While for the deep strength asphalt pavement, it consists of the asphalt concrete surface, asphalt concrete or emulsified asphalt base, and the granular base. We will observe the tensile stress applied at the bottom of the asphalt concrete layer, while the compressive stress is applied at the intersection between the granular base and the subgrade layers. To implement the AI method, we first need to define the criteria applied for the flexible pavement design. Generally, there are two types of the design criteria: fatigue criterion and permanent deformation criterion. In the fatigue criterion, we can identify the allowable number of load repetition to control the fatigue cracking. And this number is generated to make sure that the maximum allowable fatigue cracking is 20% covering of the area in the wheel path. The equation here shows the relationship between the number with respect to the tensile strength at the bottom of the asphalt layer, and the modulus of elasticity. Also, you can apply the shear equation for the estimation. The only difference is the constant coefficient. With the permanent deformation criterion, we can identify another allowable number of the load repetition with respect to the rotting effect. And the equation here shows the relationship between the number of load repetition to the vertical compressive strength at the top of the subgrade. With this number of the load repetition, we can reach the maximum allowable of 0.5 inch or 12.7 millimeter rotting. In the AI method, we can actually apply some other models for the fatigue criterion. For example, we have already introduced the shear equation where we will apply the new constant coefficient 0.0685. Also, we can use the modified shear equation, which is shown in the formula here. In this equation, the allowable number of the load repetition will be the function of the tensile strength at the bottom of the asphalt layer, the modulus of elasticity for the asphalt layer, some lap calibration parameters, and the lap to field adjustment factors, also the thickness of the asphalt layer. Similarly, we can apply different models for the permanent deformation criterion. And the equation here shows the general form of the relationship between the allowable number of the load repetition and the compressive strain and the modulus of elasticity. In this equation, Bi and beta are the coefficients calibrated from the field and the lab experiment. Also, at the bottom of this page, there are some examples about the rotting model based on the subgrade strain, and it can be applied for different rotting. Could be like 0.5 inch or 0.4 inch. In the flexible pavement, rotting is usually in the base, subbase, or subgrade stability problem, but it can also be exacerbated by poor asphalt mixed characteristics, while the cracking is the result of overstressing or weathering. Overstressing in the bottom of the asphalt shows up as longitudinal, then transverse, then alligator cracking, while weathering cracks results from dry shrinkage cracks, freeze-thaw fracture, or wet-dry cycle fracture. Shelving is a mixed stability problem relative to the imposed loads, or can be caused by slippage due to the poor bonding between the asphalt and the base layers. With this background information, we can then go to the design procedure in the AI method. First of all, we need to go through the factors we have to consider in the design. First of all, definitely we need to consider the traffic load applied to the pavement, and then we have to do the test about the material properties. For example, for the subgrade, we need to find out CBR or resilient modulus. With that, we will design the structure of the pavement to identify the thickness of each layer. And we also need to conduct an economic analysis to identify the cost of the construction and to determine whether it's reasonable for us to conduct the construction in the design area. The first factor we have to consider for the AI method is traffic loading. We have already introduced the traffic loading analysis in the previous lectures. Here we are making a brief review about the analysis. In the analysis, we define two variables, equivalent single axial load, ESAL, and the load equivalency factor, LEF. The equations here shows the estimation of the ESAL with different load groups. Basically, it's a function of the initial number of the repetitions, directional distribution factor, the length distribution factor, the design period growth factor, and the annual traffic growth rate. Also, we know that the pavement design is actually applied for the truck traffic, so we have to estimate the ESAL based on the equivalent 80 kN single axle load in the design period. The equation here shows the estimation of the ESAL with respect to the truck traffic. The first part shows the average daily traffic times T will give you the average daily truck traffic, where T is the truck factor, and then times TF, which is the mean ESAL per truck. With that, we can find out the equivalent single axle loads, and it times 365 to find out the annual load, and then it times the growth factor to find out the total ESAL for the design period. In addition, for the road with multiple lanes, we need to find out the percentage of the total truck traffic in the design lane, which is a DL, and we can identify the total ESAL in the designed lane for the design period, which is the value we want to identify for the pavement design. The table here shows the length distribution factor for the two-directional road and the different number of the traffic lanes. For the two-lane road, the percentage is set as 50. For four-lane roads, where each direction will have two lanes, then the percentage is set as 45. Actually, can vary from 35 to 48. Well, if there are more than 6 lanes, then the percentage on the design lane will be 40, and it can vary from 25 to 48. The table here shows the growth factor applied for the estimation of ESAL, which is a GF in the previous equation. It actually can be estimated based on the equation 1 plus r to the power of n minus 1 divided by r. Here r is the annual growth factor, which is the value in this row. And the design period is shown in the first column. With this equation, you can identify the growth factor with a specific annual growth rate and the design period. For example, for the annual growth rate of 5% with the design period of 20 years, we can find the growth factor as 33.06. The table here shows some typical truck load factors for different vehicle types, including the single unit trucks and multiple unit trucks. Also, the truck factor is related to the type of the road. The factors on the rural roads and urban roads are very different. In the AI method, we also need to apply the load equivalency factor, LEF, to identify the damage caused by each pass of the traffic load. Usually for the single axle with dual tires, the LEF is defined as the axle load divided by 80 to the power of 4. And the table on the right shows the load equivalency factor under different axle loads, which can be derived from the equation here. There are also some other models applied for the estimation of LEF. For example, France Pavement Design Manual defines that LEF equals K times axle load divided by 80 to the power of alpha. Here, the coefficients K and alpha is related to the type of the pavement and the type of the axle. For the flexible pavement, alpha is 5, and for the rigid pavement, alpha is 12. Also, the value of K is related to the pavement types and the axle types. For example, for the single axle, the value of K is 1 for both flexible and rigid pavement. while for tandem axial, K equal to 0.75 for the flexible pavement and 12 for the rigid pavement. In addition, the value of K is related to the subgrade stiffness and the asphalt layer thickness. The table here shows the typical values of K under different subgrade stiffness, asphalt layer thickness, and axial types. Moreover, there is a maximum load applied for each type of the axial. For the single axial, the maximum load is 58.84 kN. For the dual wheel triple tandem axial, the maximum load is 250.07. The table in this page shows the approximate ESALs for different traffic classes. For example, for the Class 1, which will be the parking lot, driveway, the light traffic residential street, the number of the heavy truck expected during the design period is less than 7,000. In that sense, we can find out the equivalent ESAL is less than 5 times 10 to the power of 3. While for the Class 6, with the urban interstate highways or some heavy industrial roads, the number of the heavy trucks could be as high as 7 to 15 million, which is equivalent to the ESAL of 10 to the power of 7 during the design period. The tire pressure of the trucks also affects the estimation of ESAL. We need to apply the ESAL adjustment factor with the consideration of the tire contact pressure. Usually the contact pressure equals to 90% of the inflation pressure. With a higher tire contact pressure, the ESAL adjustment factor will be larger. Also, if the thickness of the asphalt layer is smaller, then we should apply the higher adjustment factor with respect to the tire contact pressure. The second factor we have to consider is the subgrade material properties. We are especially interested in measuring the strength of the subgrade material. Usually the strength is measured by the resilient modulus MR of the soil within 600 mm of the planned subgrade elevation. Also, depending on the traffic levels of the pavement, the value of MR is defined as the 60%, 75%, or 87.5 percentile of all the test results for each section. This indicates that we have to conduct at least 6 to 5 tests for each section. Also, we can estimate MR based on the value of CBR. If CBR is measured in megapascal, MR is 10.342 times CBR. If CBR is measured by PSI, then MR equal to 1500 times CBR. But you have to remember that there's some limitations about CBR and the MR relationship. Usually this equation is applied for cohesive soil with the CBR values less than 20. As we stated in the previous page, the selection of the MR values depends on the traffic levels for the design pavement. Usually with a smaller traffic level, the percentile of the MR will be smaller. For the traffic level with ESAL less than 10,000, we have to choose 60 percentile for MR. If the traffic level is between 10,000 and 1 million, we need to choose 75 percentile. If the ESAL is higher than 1 million, then we have to choose 87.5 percentile. The figure below shows the distribution of the MR from different tests. In this example, the 60 percentile is 67 megapascal, while the 87.5 percentile is 53 megapascal. In addition, there are some requirements about the materials for the base and subbase layers, including the minimum CBR values, the maximum liquid limit, the maximum plastic index, minimum semi-equivalent, and the maximum percentage of particles passing the number 200C. For example, for the base layer, the CBR value should be higher than 80, while for the subbase, it only need to be higher than 20. So that's all about lecture today. Thank you very much for your attention. In this lecture, we introduced the AI method for the flexible pavement design, but we haven't finished all the contents of this method. In the next lecture, we will introduce the rest contents about this method and some examples for the implementation of this method.